Hello, my name is Abhishek Karthik, and I'm doing a video on Turing machines. What is a Turing machine? Turing machine is a mathematical model of a computation that defines an abstract machine which can implement any computer algorithm. So we've seen about finite automata, push-down automata, linear-bound automata. Now, Turing machine is the most powerful of them all. It is the most powerful automation. It was designed by Alan Turing in 1936. So what is a Turing machine? So Turing machine in a nutshell is basically an infinite rewritable tape. So it is basically a point, it has a point ahead, it is an infinite tape here which can be on which we can put inputs, we can check if a string belongs to a language and etc. And these blank spaces are identified by a special blank symbol. So here we have type 3. In type 3, we have finite automata, which can accept regular grammar. In type 2, we have push-on automata, which accepts context-free grammar. In type 1, we have linear-bound automata, which accepts context-sensitive grammar. And type 0, we have Turing machine, which accepts unrestricted grammar. So let's see the definition of a Turing machine. A Turing machine is expressed as a 7-tuple where Q is a finite set of states, sigma is the input alphabet, gamma is a tape alphabet where sigma belongs to gamma and sigma is a subset of gamma. Delta is Q cross R gives Q cross gamma gives Q cross gamma cross the directions L comma R. L is left, R is right. Delta is the transition function. We'll get to that in a few minutes. And Q naught and F are the start state and final states, and they belong to Q. And B, as I was saying, is a blank symbol, which is a special alphabet of gamma. So let's see the differences between Turing machines and DFAs and why Turing machines are more powerful than DFAs. So Turing machines can both write to and read from the tape, as I was saying, and while DFAs can only read and not write from the tape. So this alone is enough to tell us why Turing machines are more powerful than DFAs. And then the head can move left and right. The head can only move free to the right. So in DFAs we can traverse the string from the left to right only. But during machines we can at any instance we can move left or we can move right or we can stay in the same place too. And then the accept and reject takes immediate effect in Turing machines, while in DFAs accept and reject takes time. Let us see an example of Turing machine. We have a Turing machine recognizing the language P equals A power n, B power n. So the way we approach this is that, let's say we have this, so we have this Turing machine here, in which we're given this input string A, B, B, B. So we have to check if this belongs to this language or not using a Turing machine. And then the rest is blank. This is a blank symbol. Let us see this blank symbol, and this is infinite. So what we do here is we start from here, we convert this A into an X, and then we keep moving right until we encounter a B. It doesn't matter what symbol is in between. All that matters if we reach the first B. So when we reach the first B, we convert this B into Y, and then we turn our direction and we scan towards the left, and we keep going left until we encounter an X, the first X. So when you encounter an X, we move one step to the right, and then if this is an A here, we convert this A into an X, and then repeat the process. We keep scanning right. Also, we can only move one step at a time. So we start. Let's say we start from here. We go right. We check if this is A, and then if it is an A, we keep it as it is, and we go right. And then we check this if it's A, we just keep it as it is, and then we go right. We check if it's a A. If it's not, it's a B, and we convert it to a Y, and then we go left. We do all this one step at a time. So now we convert this A into an X, and we keep scanning right until we get to this B. It doesn't matter if it's an A or a Y in between. Now, this is a Y. It doesn't matter if it's an A or a Y in between. All we need is we find the first B. Then we find the first B. We convert this into a Y, and then we repeat the process. We go left. We keep scanning left. We encounter the A. We might make this into an X, and then we keep going right. We find a B. We make this into a Y. We make this into a Y, and then we keep going left. Now we don't find any A's. We keep scanning left. We ignore all Y's and X's, and we keep doing that, and we reach the left end of the tape. And when that happens, that means and then we keep scanning to the right until we reach the end of this. If we find any other B's or A's here, that means that is not acceptable. That string is not acceptable by this language. But if we keep going right until we reach a blank, then that means this string is accepted by this language. So that is a logic used. And here is the deterministic Turing machine diagram for this. So we have A, which gives X, and in the Q0 to Q1 transition, this A is converted into an X, and the pointer moves one step towards the right. And here we have a loop. So no, sorry, not a loop. So what this means that we have an A. This we keep this A as it is, and we move one step to the right. So that's pretty much it about Turing machines as an acceptor. Now, configuration of a Turing machine. So we have this Turing machine, this tape in which we have this input string, and then we have this pointer point this element. So we're in the Q7 state, and then it is pointing to this element. So this corresponds to the configuration. So where we have Q0 point to this zero, and this means the pointer is pointing to this zero in the tape, and then it belongs to Q union gamma whole star. Now, let's see defining acceptance and rejection for Turing machines. So let C1 and C2 be configurations of a Turing machine M. Definition: C1 is C2 if M is in configuration C2 after running M in configuration C1 for step 1. So let me explain this. Suppose we have the transition function delta Q1 comma B gives Q2 comma C comma L. This means that let us say we have this. We have AA Q1 BB Q1. This means the pointer head is pointing to this to B in the Turing machine. So the pointer head is pointing to this, and then the Q1 state. So in the transition function, this becomes A A C B. So the pointer moves one step towards the left, and then what used to be B here became C. So that is what this means. Q1 transition when for Q1 to transition into Q2, this B should become C, and it should when Q1 transitions into Q2, B becomes C, and then the pointer moves one step towards the left. Similarly, here we have Q1 transitions into Q2, while A becomes C, and the pointer moves to the left. So this becomes this. And here we have Q2 is pointing to the blank blank symbol, which means we have reached the end of this string. So the Turing machines can broadly be classified into two types: the acceptors and the transducers. So we've just seen acceptors, and now transducers are, as I was saying, Turing machines can be used to write onto, right? So that's what transducers do. Acceptors are used to read the strings, while transducers are used to write onto. So this is used to do computations like additions and many different computations. So acceptor Turing machine is an automation used to define Turing as acceptable language. It's used to define languages. Such a machine can be used to check whether a given string belongs to a language or not. which is what we just saw. It is defined as a seven-tuple machine. A transducer is a type of Turing machine that is used to convert the given input into the output after the machine performs various read writes. It does not accept or reject an input, but performs series of operations to obtain the output right in the same tape and halts when finished. So, few examples of Turing machine transducers are Turing machine for addition, Turing machine for ones and twos complement. So we're going to see how a Turing machine it gets a when it is given the inputs in the same tape, it provides the output after defining after computation after computing how it provides its output in the same tape. So here we have an example of Turing machine for addition. So the approach used here is we let's say we're supposed to compute 2 plus 2, which is 4. So let's say 2 is represented as 0, 0. So basically what we're doing here is 0, 0 plus 0, 0 will give us 0, 0, 0, 0. Let's see how this is done by Turing machines. So let's say we have a Turing machine, this, and then our inputs are 0, 0. And then this we have a C here, which means it is separating this two from this two. So it is separating the two inputs, and then the rest here are just blanks. These blanks here, they play a major role in this problem. Okay, so the first step is we start from here. We convert this 0 into an x, and then we keep scanning right. It doesn't matter what element is here. It doesn't matter if it's a 0 or a c. We keep going right until we encounter a blank, and we convert that blank into a 0. We convert a 0 into an x, and then we keep scanning right until we reach a blank, and we convert that blank into a 0. And then we move towards start scanning towards the left, and when we encounter the first x, we ignore that x, we keep it as it is, and then we go to one step right of it, and we convert, if it is a 0, we convert that 0 into an x. If it's a C, I'll tell you what it is. I'll tell you what happens. So if it is 0, we convert it into x, and we keep scanning right until we reach, this is a 0 here, and then until we reach a blank. When you reach the blank, we convert the blank, and we convert the blank into a 0. And then when we repeat the same process, we keep scanning left, and we until we encounter an x. After encountering an x, we move one step to the right and see if it's a 0 or a c. If it is a c, in this case it is a c. So what we do here is, this means that the addition is done. So what we do here is we convert this c into a blank. Okay, and then that's it. That's the end of the computation. So we have the output right here, 0, 0, 0, 0. And that is how addition in Turing machine is done. And here's the deterministic Turing machine diagram for addition. So basically, we have when zeros when we encounter a 0, we convert it into an x, and we move one step to the right. And then we have, and then we whatever is given, we keep ignoring it. We just keep it as it is, and we keep scanning right. And then we have C. When you encounter C, we just keep it as it is, and we go to the right. And we just go to the right, and then the same process happens. And then when you encounter a blank, we convert that as into a 0, and we start scanning left, and that's what we do here also. We keep going left, if it's a c also, and then we keep going left if it's a 0. When we encounter an x, we go to the q naught state, and then we repeat the same process until we reach c, until the next element is not until the element to the right of x is no more a 0 but a c. In that case, we convert the C into a blank, and we go to the right, and we go right, and we halt the computation, and we got our product. I mean, we got our answer. Okay, so now let's see the variants of Turing machines. So there are so many variants of Turing machines, but they're not any more powerful than the original normal Turing. By powerful, I mean they can't recognize any other different language other than normal Turing. They all still recognize the same same set of languages, they cannot. They're no way more powerful than the other. They may make our lives easier in during computation by reducing steps or making the process easy. But otherwise, they don't identify a new language that they don't identify a language that cannot be identified by the original Turing machine. So we have multi-tape Turing machine, universal Turing machine, multi-track Turing machine, non-deterministic Turing machine, alternating Turing machine, neural Turing machine, quantum Turing machine, post-Turing machine, probabilistic Turing machine, symmetric Turing machine, total Turing machine, unambiguous Turing machine, Zeno machine. So let us see multi-tape Turing machines. So multi-tape Turing machines are basically Turing machines with n number of tapes. So far, we've been seeing Turing machines with just one tape and one head. So this one has multiple tapes, and each of them have a head of their own. And we have multi-head Turing machines in which these have a single tape with n number of heads, each reading symbols from the same tape. In a single step, all heads determine the scan symbols, and right then left and then determine the scan symbols, and right then shift left, shift right, or stay. These actions are independent of any other head. So basically, we have this tape. It has multiple heads, head 2 and head 3, and none of these depend on the other head. They can just move like any other head, left or right. And here's the thing: they can only move just like the normal Turing machine. They can only move one step at a time, left or right. And then we have non-deterministic Turing machine. In such Turing machines, for every state and symbol, there exists a group of actions the machine can have. Computations of such machines form a tree of configurations that are reachable from the start configuration, and therefore input is accepted if there is at least one node in the tree that is an accept configuration. Otherwise, the input is not accepted. Compared to a deterministic model of computing where a command leads to a single action, non-deterministic Turing machines, given specific commands, allow for a range of actions. The Church-Turing thesis. The Church-Turing thesis says that any real-world computation can be translated into an equivalent computation involving a Turing machine. Every effective calculable function it's a computable function. Effectively calculable function means that functions which can be solved using a defined algorithm. Effectively computable means functions produced by a Turing machine or equivalent mechanical device. Although the thesis has near universal acceptance, it cannot be formally proven as the concept of effective calculability is only informally defined. And then we have the halting problem. Halting problem is about figuring out whether or not a given algorithm will halt or stop at some point in time. When an algorithm is run for a given input, it will either halt after some time and return the output, or it will keep running on infinitely. Alan Turing proved in 1936 that a general algorithm to solve the halting problem for all possible program input pairs cannot exist. Turing proved that any such algorithm can be made to produce contradictory output and therefore cannot be correct. Simplified proof concept. Halt of x is a total computable function which returns true if the program halts. Define g of x. If halt of x, halt of g, then loop forever. Halts g must either return true or false because halts was assumed to be total. If halts of g returns true, then g will call loop forever and never halt, which is a contradiction. If halts g returns false, then g will halt because it will not call loop forever. This is also a contradiction. Overall, G is the opposite of what halts say G should do. So halts G cannot return a truth value that is inconsistent with whether G halts. Therefore, the initial assumption that halts is a total computable function must be false. So thank you for watching my video. I hope you enjoyed it, and goodbye.